Hello everyone, welcome back. So remember, we're chugging through our list of how to find these key features of a rational function so we can graph them. Once we really at least nail down how to find these first three, we'll start actually doing some examples of putting it all together. So in the last video, we figured out how to find x-intercepts and y-intercepts. The focus of this video is how do we find the asymptotes? How do we find vertical asymptotes and horizontal asymptotes? Okay, so let's get started. Let's first start with vertical asymptotes. Those are the easier of the two. Vertical asymptotes. Okay. So let's take a look at a simple example and try to think, where should we look on a rational function to try to figure out where the vertical asymptotes are. So I'm going to say we're just going to write kind of a simple example. Okay, so let's say we have the rational function r of x. Let's say the rational function is, which one did I want to graph for you? Okay, so let's say it's I don't know, 2x minus 4 all over x minus 3. This is one of the very simple examples where we actually can just do a some quick polynomial division or some quick synthetic division to actually see this as a transformation of 1 over x. So let's do some polynomial division. Actually, we can do synthetic division. Okay, so let's put the 2 and the negative 4 here. Remember, we flipped the signs. I'll put a 3 here. So if I bring down the 2, what am I going to get? I'm going to get 3 times 2 is 6. 6 plus negative 4, what is that? Negative 2. Okay, so this polynomial is equivalent to 2 plus, looks like we get 2, I'm sorry, this is a positive 2. 6 plus negative 4 is positive 2. So we're going to get a 2 plus our remainder, a 2 all over our x minus 3. So we can write this polynomial in this form after doing the synthetic division. If you would like, we could see this as, I don't know, we could write this as, how about we write this as a 2 times a 1 over x minus 3 plus a 2. Okay, so the key thing to look at when I write it like this is I've shifted 1 over x to the, looks like I'm subtracting 3, so I'm shifting 1 over x to the right. The right by 3. And this plus 2 is I'm shifting 1 over x up by 2. Okay, and we really just care about a loose sketch of this, so I know that this 2 here is out front. I mean, just for completeness, we won't really use this when we're drawing a quick sketch, but this 2 here, this is going to vertically stretch 1 over x by a factor of 2. So, remember what 1 over x looks like? 1 over x. All my markers are going bad today. Okay, I gotta get some new ones. Use blue. Okay. Okay. So recall that 1 over x looks like this. So here's 1 over x. And what I've done is I've shifted this graph to the right by 3 units and up 2 units. So the graph of this function will look like, what have I done? I've shifted it right by 3 units. So this vertical asymptote will be shifted to the right 3 units. 1, 2, 3, so right here. And we've shifted 1 over x up by 2 units. So here's 2. Here is 2. And now the graph will be stretched a little bit more, but I'm drawing a rough sketch, so it won't matter too much. Just kind of draw it like this. Imagine it's just a little bit more stretched than this shape right here. But here's a rough sketch of this graph here, r of x, just by thinking about transformations. Okay, notice that I have our vertical asymptote. Okay, this is our vertical asymptote here. here our vertical asymptote is the line. What is it? It's the line x equals 3. This is the line x equals 3, and that's where the vertical asymptote is. Okay, but how could have I gotten that just by looking at our original function here? Well, notice here specifically for vertical asymptotes, notice that our function is undefined there. Look, if I try to plug in 3, look, there's no output. This function is undefined at 3. Why is it undefined at 3? Well, look what happens when I try to plug in 3. If I try to plug in 3, what am I going to get? I'm going to get 2 times 3 minus 4 all over 3 minus 3. I'm going to get out, what is that? That's 6 minus 4. I'm going to get out 2 over 0. Uh-oh. We can't divide by 0. Our function is undefined there. And we have a vertical asymptote there. So where should we look for vertical asymptotes? We want to look for vertical asymptotes. To find vertical asymptotes, we want to try to look for locations where the rational function is undefined. A rational function is undefined when the denominator is 0. So we're going to look for vertical asymptotes where the denominator of the rational function is 0. So that is our observation. Okay, observation. To find the vertical asymptotes of a rational function, we look for where r of x, a rational function r of x, remember it's a polynomial divided by another polynomial, is undefined. This happens when we divide by 0. This happens when the denominator is 0. So this is our observation. We're going to look for where the denominator is 0. Okay, so let's just do a couple examples. Let's do a couple examples. Okay. So for these examples, we're going to find I'm just going to write VA, find the vertical asymptotes. Okay, as our first example, let's say we have that r of x is equal to 2x minus 3 all over x squared minus 1. And also as another example, I want you to find the vertical asymptotes of r of x. How about 4x plus 3 all over x squared minus 3x minus 10. Okay, go ahead and pause the video and give these two a shot. Okay, so we want to find the vertical asymptotes. So we want to look for locations where these functions are undefined. And that happens when the denominator is 0. So what I'm going to do, and what I'm always going to do with these types of problems, is when possible, I'm going to factor. So here, we're going to have that r of x is equal to 2x minus 3. Okay, let's factor x squared minus 1. I hope you see that's a difference of squares pattern, and that factors to x minus 1 times x plus 1. So we just want to look for where values of x make the denominator 0, and I hope you see here that the locations that make the denominator 0 are as when x equals 1 and x equals negative 1. So we have vertical asymptotes. The vertical asymptotes are at x equals 1 and x equals negative 1. That's what we know about this graph. These are the locations of the x-intercepts. I'm sorry, these are the locations of the vertical asymptotes. Okay, for this next example, in a very similar fashion, we'll have r of x, that's equal to, how about 4x plus 3? Let's go ahead and factor the denominator. The denominator will factor to, I need some sort of combination of 5 and 2. Okay, the middle term is negative, so that means the bigger of the two numbers has to be negative. Okay, so I hope we can see here that the vertical asymptotes are at x equals 5 and x equals negative 2. So that's all there is to it. That's how we find the vertical asymptotes. Okay. Let's go on and try to find horizontal asymptotes. Okay, let's try to find horizontal asymptotes. That's our next job here. Okay. Okay. Let's do horizontal asymptotes. Horizontal asymptotes. Okay? There are going to be kind of 3 cases that we'll examine. But first, let's think about how are we going to look for them. So recall we had, what was it on the board? We had the polynomial r of x, which is equal to 2x minus 4 all over x minus 3. And we discovered that we could rewrite this rational function as, what did we do? This was 2 over x minus 3 plus 2. We went ahead and graphed this. So we did a quick sketch. So up 2 units, to the right 3 units. Okay. So here was our graph. A rough sketch. Okay, so when we're looking at this horizontal asymptote, how are we going to look for it? Well, notice that really what the horizontal asymptote is telling us about a function is its end behavior. Notice that as x, notice for this example, as x is getting really large, notice that the outputs of the function are getting arbitrarily close to 2. They're getting arbitrarily close to 2. Notice similarly over here, as x is going towards negative infinity, we're going to say that r of x is getting closer to 2. Now, I could say over here as x is getting really big, r of x is getting closer to 2 from the top part of 2 or from above, so I might put a plus here. Okay? And as x is going towards negative infinity, this function here is getting closer to 2 from the bottom, so I might put a minus here. But the key thing to realize is, what is a horizontal asymptote telling us? It's telling us about the end behavior. Horizontal asymptotes, what are they? This is analogous. Is it glare in the way? This is analogous to the end behavior. This is the end behavior. So it's like when we're thinking about polynomials and we talked about their end behavior, we looked at the leading term. When we're looking for horizontal asymptotes, that's the analogy to the end behavior for rational functions. So horizontal asymptotes, this is the end behavior. End behavior of rational functions. Okay. So we have a couple different cases we're going to look at. Okay. So let's do that. A couple different cases. Okay. Let's do an example. Let's say we have a rational function r of x. which is equal to, how about 3x squared plus 1, 3x squared plus 1, all over x squared minus 2x minus 3. So what we want to do here is I want to find the horizontal. We want to find the horizontal asymptotes. But this is the end behavior. Okay, so how are we going to figure out the end behavior here? We want to know what happens to r of x when x gets really big. So the big question we should be asking ourselves is, what does r of x get closer to? What is it getting closer to as I make my x values get really big here? Well, let's think about this here. Okay, so we have r of x is equal to 3x squared plus 1 all over x squared minus 2x minus 1. Well, let's use some arguments that we made for when we were doing with polynomials. So what I'd like to say that here, that this will be approximately equal to, when x goes to infinity, well, what's going to happen? Well, remember, if we're just looking at 3x plus 1, as x is getting really big, remember that this function, 3x squared plus 1, is approximately just going to be exactly the same as its leading term. So as s gets really big, the numerator is going to look a lot just like the leading term, 3x squared. And what's the bottom going to do? Well, as x is getting really big, its leading term will dominate. The x squared term will be a lot larger than the 2x, the negative 2x minus 1. So as x gets really big, the denominator is going to look a lot like an x squared. So what's going to happen as x is getting really big? This function is approximately going to look like 3x squared over x squared. These x squareds cancel. So actually what we find here, what must be happening, is that as x is getting really large, the outputs of this function are getting arbitrarily close to 3. They're getting arbitrarily close to 3. Beautiful. So that is the horizontal asymptote. The line, we're going to say the line, let's say y equals 3, is the horizontal asymptote. Okay, so now we know a lot of features about this graph. Okay, let's factor this really quick. So what is this? This is 3x squared plus 1. The denominator factors. What is the denominator going to factor to? What? Some combination of 3 and 1. The negative has to be on the 3. So what we figured out here is it has a horizontal asymptote at y equals 3. Let's sketch this. We know some features about this rational function. We just discovered that it has a horizontal asymptote at 3, at y equals 3. And let's try to think about where its vertical asymptotes will be. Its vertical asymptote will be at x equals 3 and x equals negative 1. So far we haven't pieced the whole graph together, but we know for this graph here, we know that these will be where its vertical asymptotes is, and will be its horizontal asymptote. Okay, now this was just for a specific example for us finding this horizontal asymptote at y equals 3. Okay, but we have a couple different situations here. The one I gave you here, notice that the degree of the numerator was the same as the degree of the denominator. So we have 3 cases we need to look at when finding horizontal asymptotes. What happens when their degrees match? What happens when the numerator has a larger degree? What happens when the denominator has a larger degree? I'm oftentimes going to be thinking about when I'm finding horizontal asymptotes as there's some sort of war going on with the numerator and the denominator. Sometimes their degrees will be the same, so they're going to be tied in a war. Okay, maybe if the degree in the top has a higher degree, the numerator will win the war. Okay, if the degree in the bottom is larger, the denominator will win the war. So let's write up all the possible situations that we're going to have here. Okay, in general. So let's in general try to find horizontal asymptotes. Okay. So, horizontal asymptotes in general. How to find them. Okay, so let's go ahead and say we have a rational function, r of x, is equal to p of x all over q of x. Okay, so our first case, our case one. What if the numerator and denominator have the same degree? So what I'm going to say here is that the degree of the numerator, the degree of p, is going to be equal to the degree of q. Okay, what's going to happen in this situation? What's going to happen is that these numerator and denominator are going to be tied in the war. So what's going to happen is that the horizontal asymptote will be the ratio of their leading coefficients. So the horizontal asymptote, and I'll show you a couple examples. Horizontal asymptote will be the ratio of the leading coefficients. Okay, and as a couple examples, and I'm just going to make something up. What if we have like 5x cubed plus 7x squared plus 5 all over, I don't know, how about 9x cubed plus 2x minus 9. So let's say that this is our rational function. Notice that the degree in the numerator and the denominator are the same and they're both 3, but as x goes towards infinity, well, what's going to happen? Well, in the numerator, its leading term will dominate. It'll be roughly 5x cubed, and the denominator, the 9x cubed will dominate. So, in this case, we will have that the horizontal asymptote will be 5/9, the ratio of these leading coefficients. Okay. So whenever you're tied in the war, the horizontal asymptote will always be the ratio of the leading coefficients. Okay, that's our first case. Okay. What about another case? What happens when if the numerator and denominator have different degrees? Okay. Case 2. Let's say that the degree of the numerator, the degree of the denominator is larger than the degree of the numerator. So in this case, denominator is winning the war. Okay. So what's going to happen here is if I have a larger degree in the denominator is going to dominate. Now what this means is that when I plug in really large x values, the denominator is going to be getting a lot larger than the numerator. So I'm going to have a really large number in the bottom over a really small number in the top, and that's going to be a number that's getting really close to 0. So in this case, where the denominator wins the war, the horizontal asymptote is going to be y equals 0. The denominator is winning the war. I mean, I don't know if the bottom's really big. Like I don't know. Let's say the bottom. Let's say you have pizza. You have pizza, and you cut the pizza into 12 slices. And then you took 6 of those pizzas. You're going to be happy because you have a lot of pizza here. But let's keep the 6 the same. What if we took that pizza and then, I don't know, you cut it into 100 slices. Same pizza, now it's just in 100 slices and you took 6 of them. Well, you're not going to be as happy. You have less pizza here. Okay, but then if you have 6 slices and someone decides to cut that pizza into 1,000,000 slices, 1,000,000 slices, one pizza, you cut it into 1,000,000 slices, but you took 6 of those slices, you barely have any pizza. You might as well have no pizza. It's getting closer to 0. The denominator is winning the war. Maybe as an example, I don't know, let's say we have something like, I don't know, maybe r of x is equal to, how about like 3x plus 7 all over, I don't know, how about 5x squared plus, how about 5x cubed plus 9x plus 3, for example. Well, as x is getting really large, r of x is going to be approximately equal to, well, in the numerator, the 3x is going to dominate, and in the denominator, the 5x cubed is going to dominate. Okay, notice that one of the copies of x is canceled. So this is equal to a 3 over 5x squared. So notice here, as x is getting really, really large, this polynomial, or this rational function, is going to look a lot like a 3 divided by 5x squared as x is getting really large. But as x is getting really large, notice that the denominator gets really large, the numerator stays the same. This is going to be getting closer to 0. So, if the denominators are tied in the war, they settle for the ratio of their coefficients. If the denominator is winning the war, the denominator takes over and it drags the function down to 0. Okay, the last case, we're going to say case 3. Case 3, this is something we'll examine in greater detail in another lecture. What happens when the degree of q, the degree of the denominator, is less than the degree of the numerator? In this case, numerator wins the war. Numerator wins the war. Well, what's going to happen here is we're actually going to have no horizontal asymptotes. In this case here, there will be no horizontal asymptotes. Instead, what we'll have, we won't have a horizontal asymptote. We're actually going to end up discovering that this is the situation where we get number 5 on our list, where we get oblique asymptotes. There's no horizontal asymptotes. There's what's called an oblique asymptote. So what's going to happen is the function is not going to be coming down and settling on something. It's actually going to be blowing up somehow. If the numerator wins the war, that means the numerator will get a lot bigger than the denominator. So if you think about that situation I had a second ago where you have a pizza and you cut it into 12 slices, well, if you have 6, you have half of the pizza, but let's say then you had 8 of those slices. Now that's bigger, I got more pizza. Well, what if I had 24 of those slices? So that means I must have had 2 of those pizzas cut into 12 slices, and I took both those pizzas. But if the numerator gets bigger, I get more pizza. I get a larger number. So when the numerator wins the war, I don't get a horizontal asymptote. What's going to happen is my function is going to go away from the x-axis in some sort of direction, and it'll actually settle not on a horizontal asymptote. It'll have like these slant asymptotes that they'll settle on, and we'll talk about those in greater detail. But these are the 3 cases for horizontal asymptotes. Okay, so let's just do a couple examples. What I want us to do here is I want us to find all vertical asymptotes and horizontal asymptotes of the following. Okay. So, as our first example, I'll put a couple up here. So, as our first example, let's say we have r of x is equal to, how about 2x minus 3? 2x minus 3, and how about x squared? Let's do this one here first. Let's do 5x squared all over 2x squared minus 2x minus 12. Okay, so here's our first example. Go ahead and pause the video and give this one here a shot. Okay. So let's go ahead, and the first thing we're going to notice here is I think what's actually going to be easiest for us to do is to find the horizontal asymptote. So the horizontal asymptote. Okay, the thing to notice here is that the degree of the numerator is the same as the degree of the denominator. So in this situation here, what's going to happen is that they're tied in the war and they're going to settle on the ratio of their coefficients. So the horizontal asymptote here is going to be x equals 5/2. Now what we also need to do is we need to figure out the vertical asymptotes. So we need to figure out when the denominator is 0. Okay, so we want to go ahead and factor this. So I need to figure out when is 2x squared minus 2x minus 12. When is this equal to 0? This is how we're going to figure out the vertical asymptotes. I want to know the locations where this function is undefined. Okay, well let's factor this. Let's factor out a 2. Be left with x squared minus x minus 6. Okay, believe we can factor this polynomial. So we can factor it to, I think I need combinations of 2 and 3. Okay, I need a negative on the 3. Okay, that should work. So we have our vertical asymptotes. So we have our vertical asymptotes. Looks like when x is equal to negative 2 and when x is equal to 3. So we have our vertical asymptotes. Our vertical asymptotes, I should say our horizontal asymptote, I shouldn't put an x here, I should have put a y here. That's when y is equal to 5/2. That'd be the horizontal asymptote. Our vertical asymptote will be when x equals negative 2 and when x is equal to 3. Negative 2, negative 2. So there's our horizontal asymptote and there's our vertical asymptote. Okay, let's do another one. Okay. Okay, let's try. Let's say we have r of x. R of x, how about this is 2x minus 3 all over x squared plus 1. Okay, go ahead and pause the video and try to find the vertical asymptotes and the horizontal asymptotes. Okay, so let's first find the horizontal asymptote. Horizontal asymptote. Okay, we'll notice here that the denominator is winning the war. I have a first degree polynomial on the top, I got a second degree polynomial on the bottom. The denominator is going to win the war, the denominator is going to be getting really large, the numerator is going to stay relatively small. This is going to suck the function down to 0. Our horizontal asymptote is going to be y equals 0. Okay, let's try to find the vertical asymptotes. Okay, but the vertical asymptotes happen where this function is undefined. Specifically, that's when the denominator is 0. So that's going to be when x squared plus 1 equals 0. You try to solve this, you'd get x squared would be equal to negative 1, or x squared would be equal to plus or minus the square root of negative 1, or x would be equal to plus or minus I. So here we have imaginary vertical asymptotes. But really what this means for our purposes of graphing this on a real axis, what we're going to have here is this is actually going to tell us that there are no horizontal asymptotes. This tells us that there are no vertical asymptotes. No vertical asymptotes. No vertical asymptotes for this example here. Okay, so here's our answer. Our horizontal asymptote is y equals 0. Our vertical asymptote, there's none. Okay, let's do another one. Okay. Let's say as our last example, we have r of x. Let's say we have that r of x is equal to, how about x cubed plus 3x squared all over x squared minus 4. Go ahead and pause the video and give this a shot. Okay, so let's first talk about the horizontal asymptote. Okay, notice in this case that I have a degree 3 polynomial over a degree 2 polynomial. The numerator is going to dominate. the numerator is going to dominate, and so the numerator is going to be getting really large, a lot larger compared to the denominator. So what's going to happen is this function is going to get thrown away from the x-axis. It's going to either blow up this way or it's going to blow up down. This is going to lead the function away from the x-axis. So in this case, this is like case 3. In this case, we have no horizontal asymptotes. No horizontal asymptotes. There are no horizontal asymptotes. What there'll be here, and we'll discover this more, there will be what's called an oblique asymptote. Okay, what about vertical asymptotes? Okay, the vertical asymptotes happen where my function is undefined. Well, that's when the denominator is 0, so x squared minus 4. I want to know when that's equal to 0. I have 2 methods of solving this. I have 2 methods. I could either factor this. This is a difference of squares. So this is when x minus 2 times x plus 2 is equal to 0. So I hope you see the solutions are x equals 2 and x equals negative 2. Another way to solve this, if you'd like, is I could just add 4 to both sides. I'm going to say, or you could have said x squared is equal to 4. You could have square rooted both sides, so x would be equal to the plus or minus square root of 4, or x would be equal to plus or minus 2. Either way, we get the same answer. So our vertical asymptotes are at x equals 2 and x equals negative 2, and we have no horizontal asymptotes. Okay. So that's it for this video. What we're going to be doing in the next video is we're going to start taking all these features we learned in the last couple of videos, and we're going to put them on a graph, and we're going to see if we can put this all together to finally start graphing these things. We'll see you then. Take care.